All right, friends and neighbors, I think it's time for another networking video, and we will close out our MPLS series with this one. And I think this is the third in the series, and so keeping with that number 3, we'll do 3 advanced topics with this. Now, before we do that, let's remind ourselves a little bit about how MPLS runs. So remember that we've got label edge routers. They're the border routers on the edges of the MPLS cloud. And everybody else is a label switched router. Now, technically LERs are also LSRs. And when we have traffic flowing between a source and a destination, that traffic flows over something called the label switched path. And the label switched path is identified by the forwarding equivalence class or the details required or desired by that particular flow. And we can identify a virtual circuit because we can follow the tags on an incoming interface mapped to a tag on an outgoing interface, to another tag on the incoming, and then the outgoing, and so on until we have the entire label switched path or virtual circuit. And of course, the last MPLS router along the way pops all the tags so that so that by the time you've left the MPLS cloud, the only thing that remains is the data. There's no MPLS tags anymore. And here's just another example here. And the only reason I provided this additional example is because I wanted to make sure that we realize that even though we've been talking about single virtual circuits and the fact that tags have local significance only, we also have to remember that over a physical link, there can be lots and lots of MPLS circuits or MPLS label switch paths. And so each outgoing interface may have multiple tags that it's keeping track of and multiple different destinations. And that mapping exists on all the routers along the way. So we have to remember that physical links can have multiple virtual circuits flowing over them. Now, our first big idea up is the forwarding or forward equivalence class. And we've talked about this before, but I wanted to extend this a little bit to differentiated services. So we talked a lot about QoS. We talked a lot about the manipulation of 802.1q and then the IP header and the DSCP bits. But here we can say, well, what if we wanted to extend forwarding equivalence class to the MPLS tags? And so there's a lot to unpack here. But remember that the EXP bits were there originally. The original thinking was that they were experimental, but the discussion was always going to be that they were for some kind of precedence or priority handling. So now we've got the multi-protocol label switching support for differentiated services, and so that's RFC 3270. So the whole point here, the idea is that if we were following this all the way through, we would take a layer 2 802.1q value, the precedence value that we have there in those 3 bits, and map that to a DSCP value, and then somehow we've got to get the DSCP value or the 802.1q value into an MPLS forwarding equivalence class. And so that's what this structure is all about. So once we do that, we now have this knowledge of the differentiated services per hop behavior, and so now we've got to do that in the MPLS cloud. And so there's a couple of ways that we can do this. We can say, well, the tag, the label itself is enough. So whatever label that you have, you build a policy on the MPLS routers that says, well, look, just based on the MPLS tag, I'm going to make a policy decision on that. And so all of my handling is based on that alone. Or I can have an additional forwarding equivalence class value, some kind of type length value we'll talk about here in a second, that indicates some additional bits that I'm going to use for this. And so that's what those 2 things there at the bottom are talking about. Determine scheduling treatment or drop precedence from a per hop behavior, or simply from the precedence, or simply using the tag value for precedence. Now, there was also an addition of the explicit congestion notification, and that's also extended into MPLS as well. And just as a reminder that RFC 5462 officially changed the EXP bits to be a traffic class bits. So a little bit more on TLVs. Now, in many protocols, and actually many data structures, we use this abbreviation or acronym TLV. And TLV just stands for type length value. So if I give you a whole bunch of things, I say, here's a whole bunch of details describing something, and I just gave you numbers, you wouldn't know what those numbers meant. So type length values say, when you see this value, it means this type, and it's when I give you a length, it tells you how much information is there. And that way you know how to decode it. So LDP uses type length value encoding scheme to encode much of the information carried in LDP messages. And so that means that you have a whole bunch of TLV values. And without some kind of encoding, without some kind of scheme, you wouldn't know how to understand them. And so in an LDP message, you have a whole bunch of stuff that describes the details that you're trying to convey to the router. So a couple of common TLVs would be, well, the forwarding equivalence class. When that's encoded as a 0100, now you're looking for more details that follow that. And whenever I see 0100, I know that I'm talking about a forwarding equivalence class. Whenever I see a 0200, I know that I'm talking about a label. And then status request, and then there's a whole bunch of them. But these are the common values. Now, each TLV also includes element codes that further break down the information that's being supplied. Now, if we were going to do something like diffserve, then we would have to have additional TLV information that described what you were going to do or how you wanted diffserve to be encoded. So if we weren't using just the label, we would have to say, okay, now it's time to use the EXP bits. Here's what I want you to do. And that would be a type 0901, and that's described in RFC 3270. Wow, that was really confusing and really long. So let's do an example. Here's an LDP message that I have going between my routers. So this is an LDP message, and it just happens to be an address mapping message, as you can see here. And so now I'm going to break down the TLVs. The forwarding equivalence class, well, Wireshark tells me it's FEC, but the only reason that Wireshark knows that is because the TLV type is 0100. Now in this case, I've got additional elements in my forwarding equivalence class. And so element 1 in this case happens to be coded for a prefix. And I go down a little farther and next to that second arrow and I see, hey, look, there's the network destination that goes along with this particular forwarding equivalence class. Okay, also along with this particular label mapping message, I have the generic label that's being used in conjunction with the previous information. So there's the label encoding, and the general label type is 0200. And so that's how this sort of works. You put together the TLV type, and then if there's any additional information, you have element information, and then you provide the actual details or the information provided with that particular mapping message. And that's how you put it all together. So if we were doing something like DSCP, we would tweak the EXP bits, or what we now know to be the precedence bits, if we weren't using the label alone to describe what we're going to do on our policy. All right, and so here is just a simple configuration example that would map the precedence values to an MPLS EXP bit. And so here we've got the classes, we're matching DSCP values or precedence values, and then we're just, our policy, the goal in the policy now is just to do the mapping. So we're going to take a certain particular class and set the EXP bits, and then we'll take a different class and set the EXP bits differently, and then of course we have a service policy that applies it in an interface and direction. Now our second big idea is MPLS traffic engineering. Remember that an LSP is set for a particular set of flows, or well, I should say a flow, and that flow is given a certain forwarding equivalence class that may or may not have anything to do with quality of service, right? It might just be this destination. Okay, Explicit routing is a concept that says, well, listen, I want to specify the path that this flow is going to flow over. And so right from RFC 3031, we have something like this. Sometimes it's desirable to force a packet to follow a particular route, which is explicitly chosen at or before the time the packet enters the network. That's traffic engineering. This is also related to a concept called constraint-based routing that says, listen, I want you to use these particular resources or follow this particular path. So this brings up the question, why would you want to do that? So RFC 2702 is all about the traffic engineering. And the reasons for traffic engineering is really an optimization problem. Optimization is all about how can I do things in the best possible way? How can I find the best possible answer? So a lot of routing protocols simply can't do that. Now some routing protocols will load balance. That's very helpful. But a lot of routing protocols simply don't handle congestion problems, or when your traffic runs into slowdowns or errors or things like that. Routers just simply pick the best path given the admin distance or the metric or the prefix length in order to get to a particular destination. That's it. So if we're talking about optimization, the quote that we have here, to facilitate efficient and reliable network operations while simultaneously optimizing network resource utilization and traffic performance. So if you're thinking about this, you just say, well, I've got packets that are going between a source and a destination. I want to take the best possible path that gives me the best possible performance for that flow. But the other really big idea here is that what I don't want is to have certain parts of the network to be underutilized either. I want to maximize the utilization of my resources overall. So the performance objectives that we have here, the big one is minimization of packet loss. Now, let's just unpack that just for a sec. That's why it's highlighted here. For TCP senders, packet loss is death. And why? Because TCP has to recover all of that stuff. For voice over IP or real-time data, latency is death. So we got to remember what kind of traffic that we're talking about here. Now, if we're talking about resource-oriented, what I want, imagine that you've got a bunch of routers and you're trying to maximize the performance and the utilization of those routers. Well, you don't want one router doing all the work. You don't want one pathway doing all the work. And so that's what we mean when we're talking about resource optimization. And then, of course, we always have this idea that we want to minimize congestion. And so minimizing congestion is tied right in there with using all the best paths, with forwarding traffic over all the best routes that we know, and maximizing utilization while not overusing those particular links. Now, a big topic that's related to this is the idea of congestion. Just think about roadways, right? When you have congestion on highways, well, the highway resources are insufficient or inadequate to accommodate all of those cars. Same thing with routing. We have a lot of packets, we don't have enough in the way of resources. Now, another way to think about that is, what if you took all the cars and put them on slow roads or roads that were single lane? Inefficient use. So maybe good ways to do this would be, well, I have lots of single lane highways. I'll spread out the traffic over them. So in general, congestion resulting from inefficient resource, as it says here at the bottom, if we do load balancing, we can handle a lot of that congestion. But at the same token, if we're sending too much traffic over low capacity links or lower capacity links, when we've got a 4-lane highway, why don't we just send a lot more traffic over there? But if our 4-lane highway is congested, we want to be able to send traffic onto those single or double lane highways. So that's the whole idea that we're talking about. Now, some of this stuff can be addressed with classic congestion control, right? We got load balancing, we've got ways to slow down TCP senders. We drop some of their packets and they back off. But some congestion problems, namely when we have inefficient mapping, that's what's handled by traffic engineering. Now, related to the ideas of traffic engineering is this concept of a traffic trunk. Now, in many communication architectures, trunking is this idea where we put multiple streams of traffic together. So when we talk about 802.1q trunking? Well, we've got lots of VLANs that are multiplexed over that trunk line. If we're talking about telephony, well, we've got lots of circuits that are aggregated over that trunk line. Well, now, if we talk about a bunch of flows of traffic, right, all kinds of different kinds of traffic, and we put them, as long as they have the same class, we want to put them inside the same label switch path, we've got a traffic trunk. Now, another concept is the ability of MPLS to aggregate labels or aggregate flows, and then also to disaggregate them. Routing protocols don't do a very good job of this because they don't have the additional information. They don't know about flows. They just know about getting to network destinations. So MPLS has the ability to aggregate flows or aggregate labels and then disaggregate them as well. So we have these additional ideas. As outlined in 2702, we say, all right, how do we map packets onto a forwarding equivalence class, remembering what we use forwarding equivalence class for? And then how do we map a forwarding equivalence class onto the traffic trunks? Remember that the traffic trunks, we want the same sort of treatment for those. And now, how do we map the traffic trunks onto a physical topology using the label switch path, the virtual circuits? Now, our last thing that's related here is the resource reservation protocol. There's a whole RFC about that. Resource reservation protocol, I mentioned it earlier, is a way for us to signal into the network what we want. In this case, what we want is a particular label switched path or forwarding equivalence class assigned. So we've got this RFC just for that. Now, our last big idea is going to be virtual private networks. And I want to preface this by saying that virtual private networks, if you're a networking kind of guy like me, then you say to yourself, oh, virtual private network means encryption, but that's not always the case. A lot of times we tunnel vision. We say, oh, we're talking about client-server architectures, we're talking about site-to-site encryption. That's not always the case. We're not always talking about L2TP or PPTP or IPsec or OpenVPN. Sometimes we're just talking about either tunnels or logical connections that are set up between locations. Now, when we are encrypting or when we're doing something with MPLS, we've got to be aware that we need additional tags or some additional encapsulation. In the example of a GRE, you put a GRE header around the traffic that you're trying to tunnel across the network. Now, a virtual circuit can be thought of as a VPN because it is just for that particular traffic. It's not encrypted, it's just for that particular customer or that particular flow. Now, a lot of times the VPNs that we're going to set up are tightly bound to the routing protocol, especially BGP, because we have to advertise to other routers that we have a VPN traveling over the infrastructure. So I just wanted to point that out. VPNs do not necessarily equal encryption. In fact, a lot of times they don't. So here's our big RFC on BGP MPLS VPNs. Now, there's some unpacking to do here. So consider that you've got a couple of sites. So we've got on opposite sides of the topology here, you've got sites. Now, if you have some addressing chunks or some addressing spaces that are subsets of the sites, okay, and we want to have those address spaces communicate, we might want to establish a VPN between them. And so the subset of the addressing or the subset of the traffic that we want to flow is a VPN, or that's what we're creating. We're creating this container for this traffic or these flows going between the sites. Importantly, the two sites have to be connected to the MPLS backbone or the MPLS provider network. Each VPN now is going to be assigned an MPLS label. And so in that way, the routers know how to forward this. So when the BGP distributes the VPN route, it distributes the MPLS label for the route. Now we have this concept also of trying to match the best path or the best label to this particular VPN, remembering that there might be more than one way to get to a particular destination. So that's part of the process as well. So the MPLS packet is further encapsulated, maybe with another MPLS label, so that it gets tunneled across the backbone. So what that means is that I might not have to forward or to make part of the routing the details of the destination. I only have to add to my tables the additional MPLS information. Now there's a couple of concepts that are part of this, right? We have customer edge devices. So that's the edge of the customer network, and then we've got the provider edge, obviously the edge of the provider's network. And then these two guys are connected together, and the customer edge devices have knowledge of the VPN, and the provider network forwards the MPLS tag across its infrastructure and gets it to the terminating point on the MPLS cloud in the same way that we got MPLS labels across to the different routers before. Now, probably one of the things that's toughest for folks to wrap their head around is that we know now that routers have routing tables, and we now have added MPLS forwarding tables. But what if I said to you, well, that's just one instance of a routing table or one instance of an MPLS forwarding table? What if I said we've got this whole other collection of VPNs out there, and we're going to use a different instance of the routing table for those? That's virtual routing and forwarding. So a final note before we depart here, BGP and MPLS are tightly coupled, but neither one of them requires the other. Now we're going to do some stuff on BGP, so don't worry if you haven't seen it before. But MPLS can exist without BGP. In fact, people build MPLS over other routing protocols all the time. The examples that I gave you here were on an OSPF network. And of course, the internet would still run on BGP whether or not folks were doing MPLS. All of these protocols and the integration were designed to help sort of mitigate or work with some of the explosion that we saw in the internet. Namely, one example is that internet routing table graph that I showed you. Provider networks are these massive external affairs that use BGP, and so much of the work on MPLS and in provider networks is done with tight integration between the two. And there are even RFCs that say, well, look, here's how you bind MPLS labels and the prefixes that we see on the internet with BGP. And so there's a whole set of RFCs that describe how to do path vectors and the prefixes when we integrate the two. Well, thanks for watching. Thanks for listening. That was a long one. This was a bit of MPLS with forward equivalence class and traffic engineering and, of course, VPNs. Like and subscribe if I help you out, and until next time, may your packets always reach their destinations.